Hi everyone, I'm Gursev. I'm going to start the first session of the second day, and I will discuss the basics of healthcare language models. And it's going to be a two people session. I'm going to start, and then 25 to 30 minutes. And the second session, or the second part of the first session, will be Jabir. He will discuss the small language models. So I prepared a notebook and a small set of slides. You can take a look at these. The statistics, Veysel discussed these yesterday, so I'm going to skip them. But basically, when you say information extraction by language models, we almost always start with NER, so named entity recognition, which means that we work on unstructured data or text. We just get the important information from the text. Like this case, I'm going to start discussing on the notebook. So you see that there will be different EGFR, which is labeled as a biomarker by the model. And then it's positive. So it's a biomarker result, again, labeled by the NER model. And then once you get them, you can use them to get the resolver codes like the ICD-10, SNOMED, RxNorm codes, or you can also, on top of the NER model, you can use assertion models for negation or present. There will be a lot of information in the text, but not all of them belong to the patient, and some of them are like deny. Some symptoms are not going to be present, so they will be absent. So it's quite important. Like this one, no stomach pain. So there will be pain. If you only use the NER model, you're going to get or extract the stomach pain. But if you use the assertion model, you will get more valuable information. And also you can use relation extraction models like these. So we will discuss these. The identification, we have two sessions for these tomorrow. It's quite important. HIPAA rules in the USA and similar rules in the European side. So the identification is quite important, which means that there are identifiers or important and sensitive data like the patient. You can easily change them. You can mask them, or you can use fake information instead of these. So the identification is quite popular and quite useful. And then comes the LLMs, as Jabir will discuss these. And NER is, as I said, it's normally in the healthcare models, it's the starting point. As I said, you see, there's a sentence here, a 28-year-old female with some disease and it diagnosed many years ago and uses this drug with the dosage and frequency information. So once you run the model, you're going to get that, okay, 28-year-old. So it's going to be this, we call this chunk. So it's going to be 3 tokens. They will be merged and labeled as age. And then gender, not always important. You can sometimes blacklist this information if you want. And this is the type 2 diabetes. So it's a disease, it's labeled. And also on top of the NER model, if you use the, let's say, assertion, notice that it says in the text with a history of, so it's going to be in the past. So then comes the SNOMED, ICD-10, UMLS models, and the label is clinical finding, or different models use different labels. It can be diabetes in some very generic model. It can be just a problem in some very general model. And then we have the relative date here. Again, the drug information, you get the RxNorm or NDC codes and dosages right here. Drug name is right here. And then frequency, and also we have the HCC information, which will be again discussed. And assertion, let me make it quick. So we know that there are a lot of information in the text, but not all of them will be used. So maybe the patient denies that he has any headache, or maybe the patient says that his mother had this breast cancer. So if you use only the NER model, it's going to extract all of these, but you use the assertion model to make some of them not in the final, like this data frame. So in this case, the column number 3, the assertion column, is going to give you all of these, and then you can filter for some of the assertion status. And relation extraction, like there are different models. In this case, this one is drug and dosage information and like duration, frequency information. The NER model is going to give you all the dosage, drug, duration, frequency information, and then the relation extraction model is going to work on top of the NER model to establish the relationship between different entities. And the identification, as I said, there are tomorrow we will discuss 2 sessions because it's quite important. And let's say there is no PHI, no sensitive information, but assume that the John Doe is a real patient name, and 123 Main Street is a real address. And you see that the starting text is right here. The identification model works like this, just a small information. The NER model is going to find mostly, or rule-based NER is going to find the important sensitive information, and then the identification module or the annotation is going to make the necessary changes. In this case, you can see that transformation is the final part in the on the right. So I uploaded this PDF slides and just a quick information. So if you're going to plan, or if you're planning to use the our models, I advise you to get this repo. So the healthcare repo is going to give you all the information that you need. So you always start with the number 1. It's notebook number 1. It's the clinical NER model. You're going to get a lot of information here. And the other important address is nlp.johnsonolabs.com. Demo is going to give you a lot of demonstrations, and let's say you're going to work on this one. The Colab notebook is going to give you the running notebook, how to use the model. So it's a real model running. And then the models hub, you're going to find all the models here. You see that we have almost 140,000. Just use filtering. Let's say only healthcare models, less than 3,000. Just filter for English. We have many different languages. So right now it's below 2,500, and then filter for anything you want, like you're interested in entity resolution for the models, for the resolver code. So you use models hub like this, and the docs is right here. You're going to get all the reference information from this one. So remember, nlp.johnsonolabs.com is going to get you all the things that you need. So I'm going to switch these. So this notebook is going to give you a lot of information about our models. Maybe I can make it a little bit bigger. So let me go down. So I just import the libraries, start Spark. You remember our library runs on Spark, and there is information about the architecture. And normally, any NER model works on like 6 stages. First stage is document assembler. Information is right here, and then we split the sentences. We use a DL model. There are some non-DL deep learning models also for sentence detection, and then we get the tokens from all the sentences, and then we get the embeddings. This is a fine-tuned embeddings model, our model. Most of the NER models are trained on this one, so you have to call the embeddings model first, and then we use NER JSL. So let's go to the model sub. So you just write NER JSL, just filter for models, and it's right here. So every model has a page. It's quite important. The NER JSL is like our flagship model. It's very generic, so there will be not only just you're not going to label diabetes as a disease. There's a specific label for diabetes. So you see that there will be the label for kidney disease, and then the heart disease, and then oncological items for cancer or related entities, and even hyperlipidemia, as you see. you go down and you can see how to use this model. Just copy paste in your environment and it's gonna work. And you can just get the results here, like this one, 21 day old. So the begin and end indices, first sentence, and it's labeled as age. And the model information also is right here. It's quite a small model, and how we trained this model, and then some benchmarking about the model. So I'm not gonna run it right now, but just before the session I ran it. It's working fine. So once we get it, we get the stages in the oh, I just forgot to say, yeah, it's quite easy to just use certain entities. You can just set whitelist for filtering, and you say you're only interested in, let's say, diabetes, and then you're gonna only get diabetes from the NER-JSL model, nothing other than that. And we use Spark, and this is a Spark data frame. You're gonna see all the different stages, a column for all the stages here. So remember, this is the starting point, the text, and then the document assembler sentence, the split sentences here, all the information about the sentences, and then the tokens, 200-dimensional embeddings clinical here, and then the NER and the NER chunk. And you can copy paste this one, or you can write your code for getting a data frame, and you can see that you can save it as a CSV, or you can easily use our JSON output parser. So you see that this is the token, this is the label. All means it's other, so this model does not specify any label for this one, and this is the confidence level. You can set a threshold for confidence level if you want. If you don't want to use low level threshold or low threshold values, you can easily filter for these before or after the using. So that's the number of diseases. You can easily filter for different. So light pipeline is quite important. Light pipeline, if you're not running a huge number of text, like you're not processing hundreds of thousands of documents, you can easily use light pipeline. There are two options here. One of them is just annotate, like this one. You're gonna get basic information from these, and then you can also use full annotate. And full annotate is going to give you all the details, like all the this is the, like this one, 28-year-old, begin and end indices are right here. It's labeled as an age. It's in the first sentence, in the first chunk, and the confidence level is right here. Once you get this one, this list, you can get all the information, and as I did before, you can provide or produce a data frame, and then you can save it as a CSV or any format you want. Visualizer is open source, and it's quite important, quite useful. You don't run it in a production notebook, but in the initial stages, if you want to see the accuracy or the performance of the model, you can easily use the visualizer. You see that it's open source, and it's going to give you all the, let's say this is gestational diabetes mellitus with the label here. You can easily see the problem, any potential problems, mislabels. If it says this is a kidney disease, sorry, then there is a problem here. And if you notice that there is some problem here, you can use more than one model. We use the chunk merger here. You see that in this case, I use the second model. This is a de-identification model. The identification models, sometimes we use them for not only for the identification, but they are very good in getting the dates. So I mostly use the de-identification model to get the date, and then also we use the NER posology in this pipeline. Posology is for extracting all the drug information. So what I do was, you see that there are three NER models actually here. The first one is for the identification to get the age, date, location information, and the second one is NER clinical. It's quite a useful model. one of the first actually. It only produces or provides 3 labels here. So problem, test, treatment. Any symptom or disease, disorder, syndrome, they are going to be labeled as problem. And any treatment, like drug is a treatment or surgery is a treatment, they are going to be labeled as a treatment. So this model is quite useful. So I use 3 models here, and then I merged the results. So you see that there are different options to merge. You can use sequential or like the confidence level or other options. You can check notebook number 7 for this one, but most often we use more than 1 model, especially for the identification, and then merge the results to not to miss any information, any valuable information. So quite similar to the previous one. And if you want to train your own model, please follow this link to go to notebook number 1 and then train your own model. This is a pre-trained pipeline, by the way. It's not a model, NER model. It's multiple stages, more than 1 model. This model is, or this pre-trained pipeline is quite useful. It's going to help you to get the most important or the specific model that you use. Because you see that, remember I mentioned that we have 2,500 plus models. The first response is always for the users, okay, how am I going to find the best model? So this profiling pipeline is going to help you get this one, like metformin. We know that it's used for treating diabetes. So you just run it, full annotate for this text, for this drug, just a short function here, and it's going to give you which models to use. So you see that oncology TNM staging model does not work. But we know that NER risk factors is going to extract metformin, and it will label it as medication. So I can go to the left. So NER clinical Lang test is going to can be used. We know that the treatment may mean drugs. So this pre-trained pipeline is quite useful to select the correct model. Contextual parser, I just added here, but I'm not going to discuss. It's rule-based NER. It's quite useful. So our NER models are deep learning models, but this one is rule-based. So you define the rule, and it will be very useful to find or extract the entities if they follow a certain pattern, and they don't add any time to the any additional burden to the processing time. I just switched to assertion. Remember, we discussed this one, and remember the first 6 stages is for NER, and stage number 7 is the assertion status detection stage. So we know that we just use assertion DL, and I just, oops, sorry. Again, I go to the models page to see just right here, assertion DL, and then you're going to find the models homepage here. I just want to just make sure that you understand how to follow the routine. The models page is very important to understand how to use the model and which entity is this extract. And there is an additional stage, not always you use them, assertion filterer. As the name implies, you don't get all of the assertion entities. If you're interested, you see that I filtered for present, use whitelist here. So it's gonna only get you the present entities. So normally you're gonna get many entities here, like the fever, pain, and you see that stomach pain is absent. So if you use the assertion filter, you're not gonna get the absent or possible, hypothetical. In this case, we are only get the present entities like shown right here. And there is also an assertion visualizer, so you can easily see and understand if there is a problem. So, okay. So like this one, conditional, I advise you to take a look at the present, absent, and conditional to see if it's correct. Because like the Alzheimer's disease, not the patient, but the father has these. So I'm gonna skip the identification. As I said, there are 2 sessions by Yigit tomorrow. So I will go to relation extraction. Remember, we said that again, we start with the NER model. The first 6 stages is NER. The part of speech is another stage for relation extraction, and then the dependency parser. But these three stages, the final one is relation extraction model. So we use we try to get the relationship between different drugs and anything related to the drug. So you see that I use the NER posology to get the drug entities, and then you may, just remove this one, and you can just define the relation pairs. You don't want to see all of the relation. Maybe you can just take a look at the drug and frequency and dosage and drug, or you can just say, okay, get me everything. And when you say get me everything, again, this is a visualizer, relation extraction visualizer. You're going to see, I don't like the colors, but what it says here is the NER model got Advil for labeled as a drug, and 1 unit is the dosage. So the relation extraction model is going to give you the relations here, and not only the visualizer, but you're going to get a final result like this one, or you can just define your pandas data frame like this one. So you see that the NER model gets the 1 unit, labels as a dosage, and the NER model also gets Advil, labels as a drug, and the relation extraction model says that, okay, there is a relationship between the dosage and drug here. There is another example here if you want to take a look. It's a very tough subject. It's adverse drug events. So you get a drug, you can see some side effects, and these are extracted by right here, NER ADE clinical. The model is going to get you the drug events or drug effects, and then you can use multiple RE models to see the differences. So in this case, we use 2 RE models. So the next one is going to be clinical entity resolvers. This is quite important. I mean, to get a standardization, you don't just say diabetes, but you prefer to use, the hospitals or the insurance companies prefer to use the codes. The most popular ones are in the USA, at least ICD-10, SNOMED, RxNorm codes. And you can easily use the models. And there is another session, I guess, today or tomorrow about getting these codes. So again, there is a small function here. So in this case, that may be a little, just add some additional time for processing, because you see that the resolver models use BERT, so the BioBERT model. It's not the same as the word embedding, so that's an embedding, sentence embeddings model. So you upload this one. Normally, it's gonna be like, again, go to the models hub. So you see that how to use the ICD or RxNorm model in this case. So you normally start with the NER stages, just get the posology entities here. So then just change the type by chunk to talk. Then use the BERT embeddings, and finally you're going to use the resolver model here, which runs on the BioBERT sentence embeddings, and it's going to give you, like this one, metformin, again, same diabetes drug. It's going to give you, just say that, okay, RxNorm code is this one. It's like works, you can filter, you can get only one code if you want, or the other codes are close to the close, by KNN distance. So the first one is metformin, but the metformin pill code is also provided to you, so you can use them if you want. So there is an example here for the ICD-10 codes, and there is the final session. The final stage for me is pre-trained clinical pipelines. As I said, you can use the models, NER models, and define your pipeline like this one. or you can use our pre-trained pipelines. And this final stage, stage number 7, shows you the defined pre-trained pipelines and how to use them. So at this point, I will stop and I will ask my colleague Jabir to start the presentation. Thank you.
Thank you, guys. Thank you, Gülşah. I think it's visible. Hello, everyone. This is Jabir. I'm software engineer and data scientist, and I will try to explain and cover small medical LLMs. If you are ready, let's start. So I have prepared a notebook for you, and here's our content, Spark NLP workshop repo, tutorials under the certification training, and here is the training notebook. Then you will see small LLMs here. And you can run this notebook with any small GPU machine. Right now, I am using the A100 Colab GPU. I have a Colab Pro account, and I just use the other. But if you want, you can choose T4, L4, or L40, or A10 type of GPU. You can use easily. There is no issue. Even you can run that models in your local GPU machine or CPU as well. But if you choose the GPU, it's, as you understand, it is accelerator and it will be faster. Okay, let's see our LLM information. So there's a couple of type of LLM. We call that medical small version 3. 8B model, NER based, specifically trained NER extraction here, RAC here, text to SOAP here, VLM also here. And you will see the required GPU memory. And here is the input maximum input size there. You can provide that kind of, that much of input as a token. Okay. So let's start the medical auto-GGF model. So this model, based on the PyTorch, then we convert and quantize it into GGF. And right now, this is my NVIDIA driver. So if I run it again, it's a little bit occupied. As you see, there is the same. This is the timeline of the GPU. I run all the notebooks, and how many models? I am not sure. 4 or 5 different models take that much memory. So let's continue. Start. With the one single medical LLM, this is the quantized 16 version. So I will try to 5 different tasks with the same model. Let's start. First one is the simple, basic question and answer. This is the any high school, not the high school, maybe university student can ask this kind of silly question. So this is the question, and I know the answer, and I just check the answer. Yes, nitrofurtanin is the correct answer. So this is the basic question answer. Then you can provide some information and just ask an open-ended question. You can get the question answer like this. Okay, hypertension is a blood pressure, blah, 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 against, yes, your arterial wall consisted too high. Makes sense. So question answer is the first task. Second task is, we are using the same model, by the way, and you provide a summary information in the prompt, beginning of the prompt, this is the instruction, and then you can provide your text to summarize. Then you can get the simple summarization is here. This is the summarization task. It's already done. And the important thing is, yes, NUR extraction. And also, you can add, there is a relation, okay, drug and drug reaction. So, in the previous session, you learn entity extraction, you learn assertion, you learn relation extraction, right? So, you can gather drug and adverse drug even at the same time. Like this kind of information. You don't need to extract separately, then link again. So it is the nice trick for the LLM. Okay, this is my prompt. This is the instruction, and here is the text. Simple prompt. Then I can get, okay, this is the drug name, and drug reaction is here. And also the other labels are drug, dosage, duration, frequency, and condition, symptom, other things. You can extract whatever you want. This is the name entity recognition task you can do. And also RAG, as you know, everyone probably play with the retrieval augmented generation. So same as you will provide some context and ask a question. So the question will answer from this context, right? This is the retrieval augmented. But this is the simple prompt. I will skip and I will show the next one. Okay, if you have a vector DB, I download a vector DB. I already prepared a previous session, and I just load that and ask a question. Then I get some document and merge it. Here is all the documentation. If I see all the documentation context is related to all probably 10 document. Yes, there's a 10 document here, and is related of cause of diabetes. So I have 10 document, and I provide whole document is here, my question here, and your instruction there, then answers. So I check the answers, and all the answers is in the provided context. So you can use these LLMs via question answer, summarization, name entity recognition, and retrieval augmentation, as well as text to SQL. So simple prompt, you can provide your vector, your database structure, your database table, simple table, and ask a doctor query, or someone ask how many doctors visit that day, or some kind of simple question or complicated question to ask your database. So it generates, let's check, selects distinct visit date, doctor name from the hospital table here. Yes, table here, where diagnosis equal to phenomena. Makes sense. So here is your SQL query. And this is only one single LLM, which is GSL MEDAS 4B quantized version. That's all. And size of is here, is model size. And also I will explain a little bit parameter. mPredict means to generate token, maximum token. As you know, everyone knows the temperature. If you are using the GPU, please use the higher number of GPU layers, and batch size is how many documents will process at the same time. This is a simple parameter. And also you will check our documentation. Let me, yourself already show, but if you're asking anything else, so please go to documentation, healthcare, and there is a Scala and Python docs. If, yeah, here, Scala or Python docs are here. You can set annotators. Also, you can ask, okay, medical LLM or medical small LLM, you will find all annotator is here. Let's go, let's find the entity ruler internal. So check the annotator and see, and all the parameter is here. So you will understand which parameter to which one and extra. Okay, let's go text this up. This is the spatial LLM. Just I want to show this is the instruction to subjective, objective assessment and plan. So you have a clinical doc, but you want to understand and summarize according to for these topics. So this is the spatial model. So if you want, you can train this kind of, you can fine tune this kind of model there. So here is the subjective plan. So you can extract the plan accordingly. Okay, so those are the simple text-only model. Right now, I will continue with one of multimodal LLM, but I will extract text to string, then extract NER, name entity recognition. So this is the VLM means vision LLM. So I will use simple VLM model, but I will extract text. Then I will continue with the vision model, but I want to show, okay, VLM model can do text only stuff. And this is the spatial NER-based trained model. So let's go, this is my disease symptom. And the demographic information, PHI information there. So let's extract. I will do some process. Okay. Those are disease, symptom, and PHI information, name, date, ID. Okay. So we provide one single PDF. Also, you can provide multi. Okay, this is my PDF, and we extract all different information. You can change the prompt, you can change the field, entity, label, anything else. Okay, right now, if you don't want to use a big pipeline and you want to use one single line, one single pretend pipeline, okay, this is a pretend pipeline you can choose, or you can save your own custom pretend pipeline and use like this, pipeline.transform. That's all. Provide the prompt as an input data, that's all. Get the result. And same, okay, you have a name, age, gender, whatever you want. What you want. Okay, name, age, gender, numbers, dates, blah, blah. Okay, let's jump to vision LLM. So there is a couple of vision LLM model. Those are still small vision LLM. And we will extract information directly from image. So there's an image for the doctor prescription, I guess. No, yeah. And this image contain a lot of PHI information. Okay, we call that extract demographic, clinical, and postological information, let's extract. Okay, let's see. This is the model name, and let's see the result. Okay, this is demographic information right there, and clinical information, medication information, and also the other medication. So there's a three type of the medication information the LLM can extract. Also additional. So you can provide a PDF, convert to image, and you can feed your LLM with all this kind of document. Same, simple and fast. So let's go another VLM model. So this VLM model also trained specifically for the extraction NER. So simple NER image, the pipeline is simple. If you are using the image, so provide this VLM processor for the handle image as a prompt. Then all the pipeline is the same. And okay, we provide the image and we provide a prompt. Then prompt is the schema, JSON schema. Then we got the result. So in the previous lessons, we understand name entity recognition, assertion, relation extraction, and resolver, a lot of things. And this we continue with the LLM. So everything you can, everything we want to do with LLM is possible. Simple. Those are the simple LLMs you can run in your local machine or any cloud provider. These are the simple, and you can find the notebook right there, and also you can find all LLM, medical LLM. Let me show how you can find. You can click, just click this one and go to models. There's a okay, based on the block, what's the okay? This is the question and the answer here. Model size, and we do some test for this, and you will see the comparison of the other models. So this is the GSL MEDAS model and the other GPT-4 and the other models. You will see the comparison. Okay, that's all from my side. So I will close the session and see the next one. Goodbye.
Hi, Sabir. Are you now fully done? Is it David's turn?
Yes, it is. I will try to answer if there is a question. Then in a 10 minutes, David can continue.
Okay, sounds great. Please, guys, if you have any questions, drop them in the chat and let us know. And David will continue in about 10 minutes from now if you want to take a little break.
Yeah. I think all questions already answered.
Everyone, we are starting in 2 minutes. Hello, everyone. This is David Cecchini, and I will be with you for the next session. We are going to talk about how to build patient journeys, which is another offer from Jones Know Labs that allow for multiple analysis on top of healthcare data that will be standardized. So hope you're all with me. We're going for the full session. You can make questions. My colleagues can answer while I'm keeping the presentation. So the idea of how to build patient journeys and how to make analysis and cohorts is that we need to gather the information that is usually spread in multiple sources. So that means, of course, you have multiple EHR systems that you have information about the care that was given to patients, but you can also have raw documents in TXT format, let's say clinical notes, or they are in PDF format, or they are being exchanged via a file server, or maybe they have images and other types of information like spreadsheets or APIs and other CCD and other formats. So the idea that we had is, let's make a platform where we can gather information with multiple modalities, with multiple formats, multiple structures that can have any kind of format. So they are not consistent. They have duplicate information. They have a lot of noise that we need to parse through all of it to have a single source of truth. So why we do that? Because we believe that data is usually very important. Data is present in the HR system, but they usually register the most important parts of it and not all of it. So there are multiple studies that shows that when we add data from unstructured format, let's say clinical notes, to our database, it can actually improve a lot on the quality of the data or the completeness of the data. So let's say you can see information about self-harm or tendency to suicide in text, but they are not registered in EHR system. So that's also why we have a specialized model for mental health and other aspects of healthcare. So when we parse documents, we will get all of that information, as well as many other data points that can exist when studying or when trying to identify patient data. maybe social determinants of health is not really registered in the EHR systems, and they need to be parsed through the clinical notes that mention some habits, or mention smoking, or mention other social determinants of health that is not registered. Maybe they are not associated with an ICD code, or maybe they basically were ignored because it was not the main cause of the patient visit, so they just skipped it when registered in the EHR system. So what we are aiming at is actually get all this extra information that we may extract from the PDF documents, from clinical notes and other documents, that so we will have a very complete source of information. And on top of this, a bigger database, we may add extra functionality. So that's the main idea. So when we talk about patient journey, we see that, of course, EHR data will have the main causes, or the main diagnosis, or the main treatments that were given to patients. But maybe when we add some discharge notes, we may get some extra information that was not registered in EHR. And let's say we add data coming from FHIR, that will get data from a different source, and then add to the patient complete history. So of course, on top of that, what we can do is we have the data, we can enhance the data that we have by adding extra data points. So what do I mean by that? Maybe we can register, let's say, the patient weight and height values for the patient, but given that we may calculate BMI scores, right? So we can add extra calculations on top of the data that we have. So we can use the data points that are distributed from those multiple sources, and then by checking all of them, of course, depending on what is the conditions to calculate those scores, we may use the data points to enhance and add extra points that are not present anywhere. So they are not calculated, they were not measured, they were not registered anywhere, but we can still enhance the database by adding that. So we can add risk scores, we can calculate other metrics, and even perform care site or hospital facilities scores. So we can clinical quality measures, let's say, on top of the care facilities. So why are we building something new? Is because we have a huge experience on working with healthcare data, and we are, of course, an AI company, and we went over all the NLP progress in the past years, and we were, of course, working with lots of NER models, like Gustav showed before in the previous session. So we can add relation extractions, we can add some assertion status and so on, and then we can extract a lot of information out of that. But in our initial experiments with large language models, we saw that when we are working with complex databases or complex healthcare data, those even big models like ChatGPT, GPT-4, and so on, they really have a hard time to give you proper answers on top of that. So one example is, let's say we want to perform text to SQL. So this means that I will write a question to the LLM, and I want the LLM to write me a query, let's say a SQL query, to extract the data from my database. So if we write something like find patients diagnosed with back pain that have had spinal fusion, even this simple question, the LLMs tend to get it wrong just because of the complexity, either of the database or healthcare itself. So if we add a reg system on top of that, it will also be hard to find the relevant information because there is more than one relevant information in this query that usually the query system will only get, let's say, one of them as the top record, not necessarily both of them. So if we use a pre-trained text-to-SQL model that works well on some specific applications, it will probably not do well in a complex database with many tables and many relations among the tables. So of course, there will be lack of consistency because the models are not really sure what they are doing. And by creating a text-to-SQL that can work on the text data, we can democratize cohort creation. So this is basically one of the features of the platform because it really helps non-technical people to actually have analysis on top of the database, even if they are not technical in terms of SQL knowledge or how to type those complex queries themselves. So what we're going to see next is basically how we build it and what is the different modules of our patient journey product, which is aiming at solving those points. So let's see what we are doing. Of course, this is a licensed product, so we aim at serving enterprises. So to serve enterprises, you have to have a lot of extra capabilities in terms of compliance. So let's say our data is fully de-identified, or it can be at least fully de-identified on any data that is added to the platform. Of course, we have state-of-the-art models in terms of accuracy. So we do have many pre-trained models to allow for consistent answers, and LLMs are being used in specific parts of the platform where really using LLMs is relevant and can give you the usability that you need. So we can also explain where the results comes from. I will tell a little bit more about how we can help with explainable results as well. And of course, it needs to be easy to operate, easy to integrate, and it needs to be easy to update. And so this is basically requirement for enterprise grade design. And what we want to have on top of this database that we are constructing is basically AI and BI capabilities. So you can chat over your data. So the text-to-SQL that I mentioned, it will be of course part of it, but so you can chat and get the results already. So the query is generated and the results are retrieved automatically. You can also type them manually if you are a technical person. Of course, we have dashboards to show relevant information on top of the data, and you can allow to use notebooks to connect to it and then do your own analysis if you want. The platform needs to be ready for scalability. So that means that some of our clients, they use platforms to process millions of documents or billions of documents. So that because every patient may have multiple documents associated to him. And of course, when you have millions of patients, this can scale a lot. So depending on the size of the company, you will have multiple users that will be using the platform at the same time. So everything needs to be with the best infrastructure and the best design patterns to allow scalability. And of course, at the end, we want to be based our platform on open data models. So this means that it is as industry standard, so it is maintained by by the community of experts, and it allows people that are familiar with those to get ready for analysis quick. So I'm going to talk about the open data model that we are using in a few slides. So of course, we talked about the healthcare NLP that can perform multiple data extraction from the text. So when we process documents in raw text format, we can use our state-of-the-art NLP models to find those information. So we saw before how we can actually build a pipeline, then we can create multiple models on the pipeline that would identify different entities. We can apply assertion status that is very relevant for our use case, because we are interested in what is present in the status, meaning that the user has some condition or some procedure was performed on the patient and not to somebody else, or not in the past, let's say, as an example. So those information is really important when we are doing analysis on top of the data, because we need to know if the person is having certain conditions or not. So let's say I want to create a cohort to study specific conditions, let's say breast cancer that are taking some medicine, or there are that did some procedure in the past. So I need to know that breast cancer is present, but that procedure is past, and where to look on it in my data model. So this is very relevant. So we basically can extract those information out of the text, and then we can, of course, associate a confidence value for them. So maybe some of the entities will have very high confidence, while others may have very low confidence, and we can do some analysis, or we can define thresholds on what we accept to be used in the final database. Another thing that we use is the terminology server that you are going to see in more detail in the next session. It's basically a system where we can make API calls to find vocabulary codes. So it can be ICD-10 codes, but it can also be any other vocabulary defined that is being used and is open source, or is available for healthcare analysis. So let's say we have the, of course, all of the available vocabularies from ICD to SNOMED and RxNorm, or maybe line codes and many others. So those codes are the ones that will be helping us to normalize the data. So when we are processing text documents, we may find many different observations of, let's say, breast cancer, that they are typed differently, or they have more or less words into it, and they are basically talking about the same entity, but in different ways. So just because of how people write the information. But when we have a code in a vocabulary, then of course this is the same entity, so we can basically change the information and use those codes instead. So by doing that, we reduce noise, we normalize the data, so it will be easier afterwards to find duplicated information, and we can merge and remove duplicates based on that. So this is a very important step on the system, that you basically be normalizing the data. So as I mentioned, we have a merging and a duplication step. So this will be making sense of all the noise that can come when we have NLP data, so we can extract multiple mentions to the same event or to the same entity when we are processing the text documents. And then we need to understand how we can merge them or duplicate. When I say merge, this means that maybe we have the same entity, let's say abdominal pain, but some of the records come with more information associated to it, let's say the date, or maybe the care site where it was diagnosed or something else. And then if that information is not present in the other mention of that, we can basically merge them and keep the more complete record. So, and removing duplicates means that if we have the same event multiple times, it was found in the first page, the second page, and the third page, let's say 3 times, the same event, we can basically just keep one, because we don't need to keep duplicated information at the end. So we can build Bayesian graphs and understand everything that happens to patients, so we can make those connections and build a graph, or we can basically look on the final tables that we can use to making analysis. So when I mentioned before that we can enhance the data with other calculations, of course we are using references that mention how to perform those calculations and which calculations are the most important ones or which calculations to perform. So we are supporting everything that can be calculated based on patient information or based on the healthcare or the care given to patients. But also we have modules to calculate clinical quality measures. So it's not on patient level, but is on facility level. So it's we can get quality measures of care sites based on the database that we have. So those are also very relevant measures that we can add, and those can be calculated, let's say, every year to make reports on the care sites that you are interested. So those can also help to create reports, and even for regulators that may require that information. So let's say we may have rule-based calculations. So this is maybe easy to generate, and then we have equation-based calculations. So it's harder, but also can be performed in a SQL query. It's just more complex to generate, but we can perform that on top of a full database for all patients. And you can even build cohorts based on those calculations that are created. So that means that we are enhancing and expanding any information that you have in the database by adding risk scores and other calculations on top of it. So if you are working with any of those calculations, we can, of course, create cohorts based on them. So if let's say all the input information is present for the patients, then basically it can be calculated. And usually when you have those measures in specific units, of course, they need to be also normalized by the data model. So when you have the measure added to some patients, let's say albumin or maybe sodium levels or chloride levels or bicarbonate or whatever, then we can, of course, get the unit of it already normalized. So we will not need to normalize it on the fly, or at least we will know what is the unit that we have for those columns. So it will be already be normalized during the ETL process. And of course, we are interested in keeping provenance of information. What does that mean is that, of course, we have data that can come from EHR systems. So it's structured data. It is coming from a database. It went through an ETL process that was adding it to the database. We also can process unstructured data like images, PDFs, and text, extract information from the documents, and then parse them, add them, keep the confidence levels, and so on, and then we can merge and duplicate it all to get the final database. But if we want to check either confidence scores or where each data point came from, we have the provenance, which means that we can go back to the origin of the information and say maybe this hypertension was mentioned in a specific document, and we can see here the text highlighted that hypertension was indeed present in that document. So we can match, or maybe it was a false positive, let's say, of the model. Then we can adjust and make changes in the database, let's say, if that's the case. So the database, the data model that we are using is based on the OMOP CDM. So OMOP is Observational Medical Outcomes Partnership. It is maintained by OHDSI, which is a community, it's a global community collaborating on healthcare data science. So basically, it has been maintained by them. We are currently using a version 5.4, which is the version that is suggested by OHDSI at this moment. So they are working on the next version. It's not still ready for it. And what we are following through the community meetings and documentation that they have is that they are also working on better integration of NLP data into OMOP CDM. So previously, OMOP CDM was not really accepting NLP data. They did have a Note NLP table, but to move records from Note NLP table to let's say patient tables, it needs to pass a human review and need to be done manually. So of course, we are using the common data model, but we are making it more flexible to accommodate for adding information coming from NLP. And we do that knowing that ideally everything needs to be passed through human, but in practice this is not possible due to the volume of data. So what we do instead is we keep provenance and we keep confidence scores, but we can enhance data and create more application on top of it. And given the research studies that show that many important information is actually lost in the unstructured data, we think and we agree that this is much more relevant to keep them. So and leave humans to do analysis and decide how to understand the data. So the OMOP CDM is a complex database, is a SQL database, usually in Postgres. So it is already created and designed to add data coming from multiple sources. So of course, it goes in line with our goals. And then we normalize the data into this common data model. So basically, this is the right tool and the right data model to use. and we are working on top of that. So what is how is it defined? So we are working on the CDM version 5.4. Again, which is the one that is recommended to be used. Some people that has been working with OMOP use previous versions, but usually most of the enterprises are using version 5.4. So it has 39 tables, lots of columns in each of them, and they can be split in a few categories. But we have the blue part in the left, which is basically information about a person, like our patients, is the one that we are more interested in. So we are definitely interested in visits to care sites. We are interested in conditions, drugs, procedures, devices, measurements, observations. So those tables, they are very relevant when we are talking about patient care. And of course, we keep track of notes, NLP, and other relevant information about the person. So the tables in the middle, the standardized health system and the standardized vocabularies, they are basically tables that won't be changing much. So location, care site, and provider, they are basically things that you can register in your database. So locations is like addresses or places. Care site is, of course, facilities that provide care to patients, and providers are basically the professionals like doctors that provide the care to patients. So those are usually can be optional, but if you have, it can allow for more analysis on your data. And the orange part is basically coming from standardized vocabularies coming from Athena and the vocabulary maintainers like ICD, SNOMED, and so on. So those are basically tables that are settings, or they are just to allow for normalizing the data and using the codes that we use everywhere. So concept table is probably the most important one. It's basically the biggest table, or one of the biggest table that you have in OMOP CDM, that will contain one row for each information that exists. So let's say a location have a concept associated to it, a care site has a concept associated to it, a provider, a person, a condition, everything that exists needs to be registered in the concept table. So we need to have a concept ID, which comes from this concept table everywhere. So so that's why it's one of the most important ones in the OMOP CDM model that will be used everywhere. So when we normalize the data, let's say we normalize a condition. So let's say a patient is diagnosed with breast cancer. So we need to say patient with ID 1 has condition with condition concept ID 123 that is registered in the concept table and associated with a vocabulary ID that is representing, let's say, a SNOMED code X. So everything is glued together and normalized in this data. That's why the LLMs cannot deal with such a complex database, because the relations and how the information is stored is very complex. So you will get even the biggest LLMs will not be able to perform good quality of queries on OMOP CDM because of the complexity of the database. So how is the tool actually looking like? So we don't have much time to show it live, but basically the tool is have a UI for you to do all of those analysis. So you can actually process the information, so you can complete, you can create connectors to your database. So let's say we connect an Epic EHR system to Patient Journey, so that we can set a schedule where we will be pulling data from Epic to be processed in and ingested in Patient Journey. So this means that we can either connect to databases, we can connect to S3 buckets in AWS and many other sources of data. But of course, we can also upload documents and process them. So basically, this means that we need to give some metadata information about the documents so that it will be able to be added to the OMOP CDM. This means that we need to say patient and visit information when we add a document. So optionally, you can also add more metadata information, but what is really required is that we mention which visit and which patient is this document associated with, and by having that, we can make all the required connections to the database, and then we can process it. So as I mentioned before, the platform will basically perform a few steps when we are processing the data. So of course, it will ingest the documents when given, then we will extract the information with NLP, then it will enhance it with the code. So let's say I'm mapping the events to those vocabulary codes in terminology server, and then getting extra information with metadata that is associated with it. Then we do the OMOP CDM modeling. Basically, we decide and we create the records in the correct tables in OMOP CDM, and we merge and deduplicate the record. So in the final step, we need to consider what is already present in the database, of course, and what is coming from new data that is being processed. So after we do all of the mappings and create all the relations among the OMOP CDM, we basically can determine if it's a duplicate information or if it's actually bringing new information that was not present in the database, and we can enhance it by merging them with the existing records. Let me see if you have many questions. Okay, that's nice to know that we have OHDSI OMOP NLP work group. Welcome, Daniel. So about the standard codes, yes, we do have some, let's say, process to update. So let's say we have some codes that will be inactivated or will be replaced by new ones. So this can happen, and then when this happens, we need to do a full system update. So basically searching if we have those codes that were removed and then needs to be remapped to the new ones. And so those is a complex process, but we do have this process to make the updates. So every few months we may get a new version of certain vocabularies, and then we need to do this update, or we can define when to run the updates with the new codes. Yeah, so Daniel, if you want to get connected, we can connect after the trainings as well to discuss more details on how we are doing. We were involved in the in some ways with part of the community as well. So we were seeing the NLP discussions on how to add the data, and also splitting, let's say, some columns into like start and end information of where the events are being detected in the text and so on. So we were following it. So how the OMOP mapping is done is basically following metadata information. So let's say we identify, so of course, if the data is coming from an EHR system, it's really just an ETL process. So we need to get information from EHR system, and it will give you what type of information it is, right? So if you have a condition on a patient, you will have already an ICD code associated to it, or some code associated to it. So all we need to do is basically transform it to standard code. And there are some tools to do that, to transform an ICD code to a SNOMED code that is basically the standard vocabulary for that. And then you make the transformation, and then you can have by ETL process. So you already know that the information you are getting is a condition, so it should go to condition occurrence table. But in the other case, when we are processing from using NLP, we know that our models can detect multiple types of entities. So we know that, let's say the model says that the entity that was identified is actually diagnosed, or it is a condition. So we search for the code to associate it with a SNOMED code, let's say. And if we get a high confidence on this code, then we accept it, and we can then use it for our final tables. So this means that if we have high confidence on the NER model and on the resolution model, then we can accept this information and then map it to a condition occurrence table. If the confidences are too low, we may keep it in the node NLP table for further analysis, but not map it to the person tables, like the condition, procedures, and so on. So it all depends on confidences and other rules that we have, but the processing is very dependent on this code mapping. So if we can find with high confidence a code to associate with the information that has been detected, so we will already get the metadata on this code. So let's say we can have the metadata to saying that it's a condition or it's a procedure or what the event is, so we can decide which table to fill the information. So basically using domains from the data that we have. I see another question here is if we populate only NLP tables within OMOP or real records. I don't really understand what you mean by real records. Stephen, if you can clarify that, but basically we populate all the OMOP CDM tables, the Node NLP also, but of course, if you're talking real records, maybe coming from EHR systems, okay. Yeah, so we do populate based on some criteria. So like if we identify condition with high confidence, we can use it. Yeah. what is other? What is the tag approach, Daniel? If you can clarify that. We actually did a lot of experiments, and maybe I don't remember if we did something in that regards. So the question about the stomach pain, that on merge and the duplication, basically Kritika is asking if, let's say, a patient have stomach pain associated to food poisoning, but also stomach pain associated with a tumor, will this two mentions of stomach pain be merged or not? So basically, it will depend on the metadata. So if by chance, let's say, in the same visit, the patient mentioned both cases, then it will probably be merged, because we are using the metadata to decide what to merge and what not to merge, and we are making some rules that will determine that. So basically, if I'm not mistaken, the rule to merge a condition, let's say, is having the same condition on the same patient at the same date in the same visit. So let's say if in the same visit the patient complains about stomach pain because of food poisoning and also because of tumor, it will be merged. But if it's in different visits, then it will not be merged in this specific scenario. So let's say in one visit, the patient complains about stomach pain because of food poisoning. Another visit is because of something else, and then they find out it was a tumor, but the date is different and the visit is different. Then we will keep both records. So the output, let me go on the slides. In our system, like we do have the chat capabilities. So like you can make questions in natural language, and then our system will retrieve the information that we're asking for, so that this can help, let's say, to build cohorts. And behind it, as I mentioned at the beginning, is that it's really hard for a language model to determine or to create the SQL associated with it. That's why we are using multi-agent system. Basically, they are designed on top of the OMOP CDM. So when we have a question talking about back pain and spinal fusion, we will have one agent that will say, oh, there is back pain, which is a condition, and there is a spinal fusion that is a procedure. And then another agent will say, back pain in SNOMED has this code, and spinal fusion in SNOMED has the other code. So then we may have another agent that will say, okay, so if you are talking about conditions and procedures, we need to use condition occurrence table and procedure occurrence table in our query. And then we can build the query, and then we can, of course, validate the query, review the query, and make sure the query is valid. And then we can run the query to retrieve the final results. And then we can find it, something like this. And then we find all of the sources. Let's say the source can be a discharge summary, or it can be, like, let's say, a EHR system. So we can basically get the final results, right? It can come from any source of it. And of course, we can also talk on patient level. So we may talk about one patient, and then we can see, let's say, a timeline of hospital visits or conditions and so on that is associated with the patient, and we can then make questions on that specific patient data. So we can say, okay, what are the medications that this patient is taking, and then we can filter by that patient ID, and then we can retrieve information from the drug exposure table, merge it with the concept to get the names and so on, and then retrieve it to the user. And also about provenance, which of course we can have a table of the information, but if we are interested in one specific information, we can click on it in the user interface, and then we can see, okay, the source is a specific document, and then we can see highlighted the information that we extracted. So this source, if it's an EHR system, of course, we will not have the tag, so we would just basically say where the data came from, or what is the version of the ETL process that was performed, or maybe the tables that were the origin of the information. It can be a FHIR document, or we can basically have the FHIR document here, or something else. So it depends on the source. Yeah, okay, so if we process, let's say, many documents from one specific patient, this is just an example of the type of the amount of data that one person can create. So let's say in Node NLP, we see that we have almost 6,000 events that were extracted with NLP on all of these patients' documents. And then after filtering, merging, deduplicating, and applying the criteria, right, to accept them, at the end, we found out those, let's say, 8 drugs that the patient is exposed to, 11 procedures, and so on. So we can have information about that. And of course, we can basically, if you are a technical person, we can connect to the final Postgre database and make your own queries to search for information. If you are familiar with it, want to do some analysis on top of that, you already have your queries and want to run on top of this database, you can also do that. So yeah, so let me see the other questions. We still have, if we have more minutes. Otherwise, if you have any other questions, please add them now, because actually we are out of time. But yes, so this is what we have been developing for the past months, and this will allow for multiple secondary analysis on top of those normalized data with provenance information, with confidence values, and of course PI and AI that is being applied on top of it. So thank you all for your attention. We will have another break and continue in the next session. Thank you.
Thank you, David. We'll meet in, let's do 8 minutes. So we'll meet at 2 p.m. Eastern. I had a few emails from the participants regarding the Generative AI Lab access. You will get access right after the training. As soon as the videos are processed, I will send you an email with recordings. And then there will be instructions on how you can access Generative AI Lab. And if you have any issues accessing it, you can shoot me an email or NS, and we will help you with the login and password. So just stay tuned. You will for sure get access after the training. And let's meet in 8 minutes. I will be playing the next session for you guys. All right, I think we can get started. This is a pre-recording since not everybody could make it today and Rakshit had to be off, but please feel free to put any questions you have in the chat and our team will address them.
Hi everyone, my name is Rakshit and I work as a data scientist at Johnson Labs. Today I'll be walking you through one of our recent products, the Medical Terminology Server. I'll start with a quick overview why it exists, what problem it solves in the real world scenarios. Then we'll explore its capabilities from both like a user perspective and the API perspective as well. So by the end of this session, you should have a clear picture of where the terminology server fits in the healthcare technology landscape and how it differs from the traditional NLP or LLM-based approaches. So let's first start with what is the terminology server. So a terminology server is a specialized search engine for medical terminology. So think of it like a Google for medical codes, but much more intelligent. So instead of searching the whole internet, it can search across the official medical vocabularies like ICD, SNOMED, LOINC, RxNorm. But unlike the regular search tools, it doesn't just match the text literally. So it understands the meaning of the medical phrases, whether someone types heart attack or MI, which often relates to myocardial infarction. It can recognize all the point, like it can map to the same medical concept, whether it's MI or myocardial infarction. It converts the clinical text into the standardized medical codes. So it acts as a bridge between the free chunk and the structured codes that could be needed for analytics, billing, or research. So when someone enters a phrase like high blood sugar, so the server maps it to the correct vocabulary, or you can say it can also map to a OMOP standard concept, which is widely accepted across systems. So this conversion is crucial in healthcare because most systems don't understand the natural language. They need codes to operate consistently. And it's designed specifically for the healthcare data workflows. So unlike generic NLP or keyword-based search tools, TSA is built with real-world clinical usage in mind. It handles spelling mistakes, acronyms, shorthand, or sometimes even like patient-friendly language as well. So it allows the organization to set guardrails, for example, searching only within the drug codes or only retrieving the codes that are valid in OMOP or FHIR, which is like a standardized system. It's just a lookup tool. But it's controlled, configurable engine, so it can fit directly into your coding environment. So now let's talk about why the terminology server was built. So the traditional coding tools rely on exact matches. Historically, like coding systems and HR would only retrieve a code if the user typed in the exact phrase found in the vocabulary list. For example, if the chunk says gastroesophageal reflux disease and the user types GERD, the older systems may not return any results for this. And this also creates some frustration, and it also slows down the work, and it often leads to incorrect or inconsistent coding. The clinical language is always messy. They have a lot of abbreviations, typos, variations. So like the real world clinical documentation is far from standardized. Doctor write hypertension as HTN or high blood pressure as high BP. So, and they all mean the same thing. So patients describe sugar problems, diabetes, or high glucose. It's also a system that depends only on keyword matching. Will if a system that depends only on keyword matching will probably miss a large portion of these variations. So that's why the terminology server includes built-in synonym spelling corrections as well, and embedding based similarity search or semantic search, so it can understand the semantic meaning of the chunk with respect to TV. So it can interpret what human mean, not just what they type. And then it needs a smarter context-aware search system. This is where the terminology server shines the most. So it doesn't just perform text lookup. It applies the clinical intelligence. It prioritizes the medical relevant matches, understand the concept relationships, and even restrict or bias result based on the context. We'll talk about it more in the upcoming slides. So it's more like only returning the drug codes when searching for a prescription workflow. It's built to mimic the decision making of a trained medical coder. So it's very much consistent with that. So it can recognize the context that you shared with them, and you can enter the chunk which is in the context. By context, I mean you can just enter a sample sentence which contains the chunk, and it will recognize the context and have the semantic meaning of that particular chunk. So for the on-premise deployment, firstly, so it can run entirely inside your secure environment. So it's one of the advantages that it's just not like a cloud-based service. It can be fully installed on-premise. So that means all the data processing happens with your own infrastructure behind your firewall. So for hospitals or pharma companies or research institutions with strict requirements, this makes adoption far easier than the cloud-based services. So you can install the terminology server with one-line command script with a license. So you'll need a license to install it. So the setup process is intentionally streamlined. So as long as the server has Ubuntu 20 or higher and basic command line tools, so the script that it uses, let me show you. If you go here, you have the on-prem deployment installation guide. So like if you go to home or if you go to docs, then there will be a documentation for terminology server, and you can go to deploy on premise. So this is the command that you need to run, and you also need to have the license key from JSL in order to run it in your own local system. So the first setup may take some time due to downloading the vocabulary data. So it's like a huge database that we curated from our own personal data sets and some open source data that we got. So we have all the synonyms, most commonly used abbreviations. So, but it's all completely automated, and you just have to just run the script and it will be ready in your system then. You can also refer to the documentation from the Johnson Labs website. The web UI and the API are available immediately after the setup. So once the installation is complete, the access is instant. So you can open the local host or your server's IP in browser, log in with the credential provided during the installation, and the full interface is ready from there. User can manually explore the terminology concepts via the UI, and the developers can connect programmatically through REST API. So no additional configuration is needed to begin searching. So you just have to run the command and it will be automatically configured in your system. The UI and the API will work as well after it's done installing. Let's talk about the key capabilities like in the high level overview. So it understands both exact and fuzzy clinical phrasing. So a user doesn't have to know the official medical term in order to retrieve the code. So whether someone types breathing difficulty or shortness of breath, TS can find the correct matching code by combining the keyword logic with the embedding-based semantic understanding. So it can also find the exact match and the similar matches. With that, you can also define how many matches you need in your search results. So it supports multiple vocabularies in a single search. So instead of requiring users to pick ICD versus SNOMED, TS runs across all the available terminologies and let you decide how to group or filter the results. So maybe a clinician wants to see ICD first, while a researcher more care about the OMOP standard concepts only. So both the scenarios are supported. You can filter with as much vocabulary as you want. So it can also filter and constrain by the domain and the code system or the validity or the standard concept, like the TS gives like the organization control. So you can set rules that you only that only drug codes should appear when I'm searching in my workflow, or only the active codes should be returned when working with the standardized data sets. So you can have we have a standard filter which will only give you the codes which are standard for OMOP or some other coding systems. The vocabularies and the concept map feature. So we have all the major vocabularies. If you see here, we have all, I think, 16 vocabularies. So you will get all the standardized vocabulary that are widely acceptable. So we have a feature which is concept mapping. So like a single medical code from a source system may be mapped to one or more codes across multiple target system. And so like it's like a curated concept maps and it shows exact and exact match from the source system to the target system, and the relationship between the different coding systems. So it's like a pre-built dictionary and it's maintained by us. So it's just not like guesses, they are all rule based. So if you provide a source code for ICD-10 like E11, and then you can select which target system you need. So by default, it will search through all the target systems. So if you want to filter them out, you can also choose the target system. So particularly these mappings are vital when you are consolidating records from different healthcare systems or migrating the EHRs. So it depends on the user's use case. And we have a UI that lets you see how the concept translates across vocabularies in real time. So let's talk about the search capabilities of the terminology server. So either you can enter a medical code and retrieve its equivalent concepts, or you can enter a particular chunk and retrieve its particular code. So this feature is called the code search. So it lets user to enter a specific code, like for E11, ICD-10, or type 2 diabetes. The terminology server returns the code's equivalent or related entries in the other code systems. For example, from E11, you can get matching concepts from the vocabularies that you select. You can also search with the clinical phrases using both exact match and the semantic search. So this is the main thing that we usually use in our products. So we are already using this TS in our internal projects. So if you enter any chunk like high blood sugar, so or imagine a spelling mistake like in diabetes you have entered you missed some uh, alphabet between them. So, but the terminology server still knows what you mean. So it uses two types of matching: exact string and semantic embedding search. So the embedding model captures the meaning. So even if the wording is uh, imprecise, the server will find the clinical appropriate codes. And the search results are deterministic, meaning you will get the same matches consistently every time for the same input, which is important for in clinical workflows. We also have Boolean logic, so like a clinical domain filters and the context tags to narrow down or like prioritize the search results. So our search engine offers some advanced tools to tailor your results to your exact needs. You can use the operators like and or in your search. For example, lung and cancer, or stroke or TIA. You can filter by the clinical domain. For example, limit the results to just diagnosis, procedures, or medication. And here the context tags helps too. So if you mark a search as coming from a medication record, the terminology server will boost drug codes in its ranking. So these features ensure that the results are not only accurate, but it's relevant to the task in hand. So in short, if you search for a search using the cancer or lung or cancer and lung, it will give you the codes related to both of them, like whichever operator that you use. Now comes the uploading the custom value sets or domain specific filtering. So you can upload your custom list of codes grouped by a clinical theme, task, or a specialty. So a value set is essentially a named collection of medical codes, like a curated playlist. For example, you could create a value set called breast cancer diagnosis and include ICD-10, SNOMED, or mesh codes that relate to that particular topic. Or you might have like cardiology medications, for example, set made for only the RxNorm. So these sets can be created manually in the terminal server. Like you can upload a CSV or Excel. We have a format for the value sets, which I'll show. So they are perfect for understanding the workflows, building the rule sets, or supporting like the phenotype definitions in the research. So we use our value sets as filters to restrict search restrict the search results to relevant concepts only. So once you successfully uploaded the value sets, it will be like a part of your search environment when it's active. So it will highlight or include all the results that match the codes from your selected value sets. Let's say you search for chemotherapy and you have some oncology specific value set turned on. So your results will be limited to the codes in that value set. So it removes the noise and the irrelevant matches. So it makes it easier to ensure the clinical relevance. You can also track the versions and the changes to the value sets over time. So you can check which value set has which version. So you can also update it. It will have a version 2 of it. So it just means that you can update them and keep track of your changes. So this is mostly required in large teams or like a regulated environment. So if you are doing a study which uses version, for example, 1.3 of value sets, and and someone later updates it to 1.4. So both versions are still available. You can trace what was changed. So this ensures like a full transparency between the people. Let's now talk about the terminology service versus the OpenAI LLMs. So that the terminology server delivers like a deterministic code-backed outputs, whereas the LLMs generate variable responses without guaranteed terminology accuracy. So this is one of the biggest philosophical differences between these two approaches. So TS works like a validated lookup engine. So if you enter a term today or next year, you will receive the same standard code because it relies strictly on the official terminology database. Like the code can change if the validated database has some changes in the codes like Athena. So we usually keep it up to date. So like the LLMs like GPT on the other hand generate free-form responses. Even with the same input, they may return slightly different code on different runs, and they have no direct access to structured or up-to-date medical terminologies like ICD or SNOMED unless explicitly provided in the context. The TS offers fixed licensing, on-prem deployment, and full privacy control. And LLMs are cloud only and metered per usage. So TS can be deployed entirely on your system, making it suitable for healthcare environments. The cost of the model is stable regardless of how many lookups are performed. So even if you send 1,000 chunks or 1 million chunks, the cost will remain the same. Whereas with LLMs, every request incurs usage cost, and all the inferences happen in the vendor's cloud environment, which introduces both financial unpredictability and the compliance barriers. TS also provides the UI. So it has the UI and the API support with various features, as we already talked. So whereas the LLM offer only the API access with no terminology model backed from behind. So TS is designed specifically for terminology exploration. So it gives user a graphical interface to browse, inspect mappings, filter. So LLMs do not natively understand the code systems or hierarchies. They only respond to free text instructions. So any terminology control must be manually enforced either via prompt engineering or like connecting it to external system, which can be a hassle sometimes. TS excels at like the precise term level mapping, whereas the LLM excel at the document level in inference and abstraction. So this is where the two tools complement each other. So TS is the right choice when you need to map a single term or a phrase to an exact code. So it does not try to interpret a broader context on purpose, but we can still do it with our context-based searches, which I'll show you. So the LLM thrive when you provide full clinical notes. They can infer likely diagnosis, procedure, or medication, even if it's not explicitly stated. However, that abstraction comes with variability and reduced explainability. TS stays continuously aligned with the official vocabulary updates. The LLM knowledge is static and may lag behind. So our TS database actively syncs with verified coding systems and distributions, and it reflects the latest terminology revision. So we keep on updating it when we have some changes in the codes, or some codes are depreciated, or some codes are not valid now. We keep our DB up to date. So LLMs, on the other hand, are trained on frozen data sets and may not recognize newly introduced codes or that depreciated terms unless it's fine-tuned or manually corrected. So this is the comparison with TS with respect to using the LLMs. Let's now go to the UI. So I can walk you through how to use the UI effectively. Now, if you want to see the documentation, you will need to go to the Johnson Labs website, and you need to go to the talk section, then the terminology server, and you'll find all the documentation, what all features that we have here. We have the installation guide, on-prem installation guide. You'll need a license for this, and you need to run this command in order to have the TS right in your machine. There are some recommended configurations that we have. So you need the Ubuntu 20+ machine, and the TS service uses port 80, so it expects the port to be unused. So the minimal configuration is 16 GB RAM and 8-core CPU and 300+ GB storage. So if you have a bigger machine, the responses will be much faster if you want to process millions of chunks in bulk. So the ideal configuration would be 32 gigs of RAM and 16-core GPUs for decent performance. But again, you can always upgrade from this as well. So it can open on Apple Safari browser, the UI, Mozilla Firefox, and Google Chrome. We also have the API service access and the API documentation on how to use the API. We also have a notebook for that. I'll walk you through. We also publish our release notes here. Like this version, current version is V3. So you can see all the changes that are included in V3, but all things have been changed. Now to go to the terminology server UI. So we have one demo server running. Right now you won't see this because we'll need to add you to the approve user. I'll just log out from here. So you'll see this page open up, and we will have to write our credentials here. If you need to test it, you need to get in contact with our team, and we can create a new user for you in order to access this URL and in order to use it. So you can, I can also create user. Let me just log in my admin. I can create and manage users from here. So right now, like we have 3 users, and I can create a user for someone who needs to use this service in order to test it. So we can provide you with the credentials. Now let's go to the main UI section, which is the search feature. So let's first talk about the code to code mapping. So it means that you can map from one code to another code in different vocabularies. So for example, if we enter let's say E11 here, and we will get all the results. To have the code to code mapping, which is hopping from one vocabulary to another, you will need to select the code system. So E11, let me select the ICD-10. No, sorry, not the code system, the concept maps. The code system are the filters that we use in order to get the data output. So for the code to code mapping, so the concept maps are used. So the concept maps means like E11 is from, for example, ICD-10, and we want to map it to ICD 9, mid-DRA, mid-DRA PD or LLD or SNOMED. So you need to click the map codes here first. Enter it again. So you'll see the source code system, which is ICD-10, and it's also ICD-10 CM. So this E11 maps to mid-DRA, PT or LLD, and the UMLS. So if you want that this code source system is ICD-10, and you need the UMLS mapping or the mid-DRA mapping, you can just select this from here. So if, for example, E11, I want to map it to mid-DRA LLD, I'll just click the search, and you will end up with the source code and the target code system and the target code value. So this code maps the coding system ICD-10 to this code in the target code system mid-DRA LLD. So this is how the mapping of the codes happen in terminology service. Then comes our main functionality. Let me just uncheck this. If it's all unchecked, you will have this search bar, which can do exact match search or the semantic search. So if we enter here diabetes, it will give us exact matches first. So the concept name, diabetes, and you will see the things related to diabetes from all of the vocabularies. So it will have the results related to the diabetes chunk. And if you want to filter it by certain vocab, so you need to go to the code systems. The code systems are all the vocabularies that we provide. It also has some OMOP vocabs. And if you want to only see the SNOMED code, SNOMED results for the diabetes chunk, we can just click the filter. You can also add multiple filters. For example, if we want to search with LOINC, we'll just add those filters, and then we'll end up with those results only. So if you see here, this is the LOINC code, and it will have all the metadata regarding it, like the concept code, validity, standard concept, chunk, domain. So for example, this is the hierarchy tree. So we need to find which one has the hierarchy. Okay, so similar to this. So this one will be the parent concept, and these are all the child node for the particular chunk. So the hierarchy is more like, for example, diabetes mellitus. It can refer to so think of it as a parent chunk, and it can also have the child chunks as type 1 diabetes, type 2 diabetes, and that's how the hierarchy is decided. So you can also see like which one is this? Diabetic education procedure. And you can, if you want to see this code, what it means, you can just click it. So you'll see the code procedure here. And the previous code was also diabetic procedure. So it's just a child class of it. So this is also another functionality, like you can also search the code here directly. If you search E11, it will get the E11 results. So let me show you. It's selected LOINC. We need to uncheck this. It's ICD code. Okay, yeah. So you see here the ICD-10 coding system or ICD-10 CM. So it has the E11 concept code. So you can also search via this. So this is the search functionalities, and let me just enter it again. VPs. You can filter it by, we have all these filters. If you want just the exact search, you can just click the filter here and search on it, and it will only result with the exact matches. And if you want all the matches, you can click the semantic search. It will have all the semantic searches. And the default search here means that you will get the both exact match and the similarity search. So it first will be the exact matches followed by the similarity search. You can also filter it by various other things like domain, is condition, drug. We have all these domain IDs in our system. And if you want to just include the standard concepts, you can just check that and you'll end up with the standard concepts only. And if you want to like get only those columns which you need, you can do it from the column section. Like if you do not need the concept name, or if you don't need the validity, or if you do not need the standard concept, you can just filter this out and save your changes. And you can also download it. You can check all and then just download from here. You'll end up with a CSV of your own. So, so this feature, the context resolution feature, is like a context-based search. So it is ideal for clinicians or coders or researchers who need to retrieve highly specific coding information, like tailored to their specific healthcare scenarios. So it narrows down the search results by filtering them by term weight. Term weight will be the weight of the chunk, and the scope will be the number of words we are taking, like from the left of the chunk and the right of the chunk. So, and then we calculate a weighted average embedding between the scope and the sentence, and we get the output. So let me think of a sentence. The patient has hypertension and complains about headache. So if I want to search the code for hypertension, the search API that we had will probably give all the exact matches and all the similarity search for the code hypertension. But if you search hypertension here, and you can choose the chunk term weight according to you. You can also set the scope to 4. For scope 4 means it will take 4 words from the right and from the left. So it will have all the context. And let me clear out the filters. So if you see here, we just searched hypertension, but it also gave us headache, which is in the context. So this is how we use the context resolution. So you can use the higher term weight when you're confident in your terminology, or use the lower term weights when the context is critical there. So you can adjust the scope based on how much surrounding text you need to affect its meaning. So, and you can also always combine it with vocabulary filters and all these filters to narrow down the search results more. So instead of relying solely on the keyword or the phrase entered, so this feature enables us to specify the additional informations like these filters as well with respect to the context resolution. So like it's a powerful feature that that sometimes enhances the accuracy of the relevance of the search results by allowing the users to include additional context when searching for medical terms. So this is also one feature that we have. Now let's talk about what was the Boolean search. So the Boolean search just uses and or operator between the queries. You can enter diabetes or lung cancer. So the results will have the diabetes codes. Okay, so we need to clean this up. We enter SNOMED. Oh, it's R. So for OR, yeah, you'll get the results for like one of them. So it can either give the diabetic result or the lung cancer result. So you need to choose the operator according to your use case. Right now, this only gives us top 20, but in the API, you can get as many as you want. For example, if we have here the diabetes and the lung cancer, it will give the results regarding the lung, diabetes. If you see here, it has lungs or diabetes results in the output. At risk of diabetes, lung cancer. So this is one more feature, which is the Boolean search. And then we have the spell checker feature. I think you already saw it before it popped up. How it works is like if we enter a typo like hypertension. So this chunk is wrong. So our TS should probably give us the suggestion for it. It says, do you mean hypertension? If yes, you can just click on yes and it will search the correct one. So right now, if you see the results are bad here, but if you just click the hypertension as yes, you will see the search results being changed. So if you see here, the concept name now is the hypertension, which is correct. So this is how we filter by, this is how we correct our spelling. So it will probably pop up when you will have like abbreviations. So let's try one abbreviation, T2DM, type 2 diabetes mellitus. And it will, so here, if you see, we just entered the T2DM, which is an abbreviation, and we got the concept name for it and the concept code. So it can also work with abbreviation or let's say difficulty in breathing. So the difficulty in breathing gives us breathing difficulty, all these concepts, and you can always filter it by the vocab. So you'll get the ICD-10 CM code. And if you just want to see it as a condition, you can just have the condition domain filter on and search it. So the domain will always be condition. So you'll get all the results of difficulty in breathing and the domain condition in the code system as ICD-10 CM. So this is for the search functionality. Then comes the value set filter. So you'll have to upload your value sets from your system. I already have one here. I uploaded it. So this is just a dummy one to show you the data might not be correct as well. But we have the domain, the custom code, the custom term, the alias name, the standard code for it, and the standard term. So For example, if we search this particular chunk, so we get type 1 diabetes as an output, and then we can filter it by the value sets. Do I have some filters? So let's remove this. You can click it from here. This is the version 1. You can also upload more versions to it. And when you just click the value set feature and click on search, so by default, you will see all the similarity search results or the exact match search results with the value set column here. So if you see the ICD-10 for type 1 diabetes mellitus, E11, we have the custom code. Oh, I mistakenly clicked it. Let me do it again. Yep. So for the value sets, if you see it's E10, you can also view the value sets from here. So E10 is this term, and we have the custom alias name as T1DM, type 1 diabetes mellitus. You can see the custom code, which you can use, the custom system. You can also have it in the CSV, the preferred term alias, and the standard code and the standard term. So if you want to just see the value sets results, you will need to go to the filters again, and you'll have to click this filter by value set to just include the value set results in the output. After clicking it, you can hit on the search and you'll get this result here. So let's try with something else, like this one. So you can also enter multiple in the UI as well. So here we end up with all the value set codes for that particular concept code. So this is how the value sets work, and you can also share it with the user. So for example, this is the version 1, and you want to share it with some other user which is using the terminology server. You can add it here, or you can share it with all the users. You can enter the name, email, and confirm. So it will be available in their system as well. So it's useful for the research purposes there. So this is pretty much about the UI functionality. We also have the API service access. So you will need to get the access token or the username or password to generate the access token. So it's similar to how I generate the users for it. So after I generate the user, you will get a username, password, and you can just enter it here, and the API will work in your local system. Now let's go to the API. So the notebook is in the Spark NLP workshop inside the certification training notebooks and the terminology server API. Let's open it in Collab. So you'll need the base URL as the terminology .demo.johnsonlabs.dev. So this is our demo server running, and you will need to have the access token. To get the access token, you will need to have the username and password here. And this notebook has the same things which I mentioned in the UI. So it has code mappings, which is if you want to have the code maps, you can enter the source code E11, E14 and run it. You'll get all the mappings. This is the API output that we get. You can specify the source code, the source vocabulary here as well. And you can also have the target vocabulary as mid-array or something else, whichever you want. And it will give you the same output like we get in the UI. So for the term to code mapping, we have this search functionality, which is same as in the UI. You'll have all these features, and you can also tweak the how many results that you want for that particular chunk. So you can just search diabetes and run it, or you can also have some features like the filters like standard concept. Okay. So you'll end up with all the standard codes. You see the codes are standard. You'll see two coding systems, source Athena, and sometimes you'll see the source as JSL. So it is coming from our own resolver datasets, which are curated. It has synonyms, abbreviations, etc. So these are the two sources where we get the data from. So one is Athena and the other is our resolver datasets. And similar to this, you can use all the things which I mentioned in the UI in the same way. You can refer to this notebook as well. We have all the features that I just talked about. It's just a simple API call. You have all the filters already in this notebook. So it's just doing the same thing, but with API. And you can always pass in a list of chunks in the query, like diabetes or lung cancer. You just have cop k is equal to 1. So it will give us the output diabetes or lung cancer. So you can refer to this notebook if you want to see the API usage. And that's pretty much about it. So that brings us to the end of the session. Thank you for your time, and I hope this gave you a clear picture how the terminology server fits into the real world workflows. So thanks again, and have a great day.
All right, that brings us to the end of the session 3, and we'll take a short break, and let's be back at 3 p.m. Eastern or noon Pacific.
Hi, everyone. We'll start in 1 or 2 minutes. Thanks. Okay. Hi, everyone. Thanks for joining in. I'm Hasham. I'm the lead for the risk adjustment products, which include HCC coding, medical coding in general, but more specifically, HCC coding, RADV audits, and DRG validation, etc. And in this session, we'll be going over the HCC coding product, as well as the RADV solution. Yeah, so first we'll go over some of the basic stuff. I'm sure a lot of you would already know what value-based care is, what HCC coding is. If not, then I'll just briefly cover those points, and then we'll see the UI, the demo, the product. After that, we'll jump over to RADV and the need for RADV and the product. Okay, so let's get started. Yeah, to start with, what is risk adjustment? What is value-based care? What is HCC coding? So basically, we have it's a shift from the traditional fee for service. For example, if somebody goes to a doctor, what they do, and if a person goes through a procedure, the doctor basically charges for the procedure that they have performed, right? So you go in, You see, for a condition, you get treated, the doctor gets paid, and you pay. That's the simple fee-for-service module. You are looking for a service, the provider provides you a service, and you exchange. Obviously, you exchange the monetary aspect of it. This is now, there are a few issues, which is why now we're moving to value-based care. So what is value-based care? In value-based care, the idea is to force the provider to provide the best service in terms of anticipating what the patient needs by looking at their history as well as trends, and suggesting preemptively stuff like, for example, if a person is of a certain age and the doctor thinks that they need to have mammogram done, then instead of waiting for this patient to come in and have their mammogram done, or even worse, wait to a certain point that requires a mammogram, the doctor would actually preemptively try to suggest mammograms. And this is all done using a score, which we call RAF score, which is based on certain basically certain factors, which we'll look into later. But yeah, that's the core difference. The main thing is in fee-for-service, it's a one-to-one tit-for-tat model. There's very limited accountability, of course, because you go in, you get treated. Simple as that. It's simple, of course, because the initiator is you, and you go in, you pay. Simple. So it's very predictable in terms of the codes that are billed. The value of those codes is very is predetermined based on obviously a number of factors, insurance, et cetera. But yeah, in the case of value-based care, basically, as I said, we have to anticipate what is the risk factor of a person. If a person, for example, is 65 years above, then what we do is holistically look at their entire history and check if they have any chronic conditions. So if they already have diabetes, then everybody knows that if you have diabetes, then the complications of diabetes are much more prevalent. That would later on occur, more or less. The probability of complications is really high when you're already diabetic. That's the main point. So you already are at risk of developing certain conditions that a non-diabetic person might not be at risk of. So this is that risk adjustment factor. And this is the whole value-based care. The idea is for certain chronic conditions that lead to extra spend in the future, as well as that lead to more complications in the future, the idea is to preemptively model them and suggest procedures, adjust billing, set a quota for their total care cost, so that everything is accounted for at the very start of the year. It's a yearly based thing. So basically what happens is based on whatever conditions a person has, a risk score is calculated depending on, of course, all the conditions that they have. Let's say type 2, if a person is only diabetic, then the score would be lower, and of course their payment plan would be a bit lower. If a person has CKD, chronic kidney disease, then of course that's a much more acute issue. Then of course their overall spending of that entire year is projected to be much more, so their payment changes, et cetera. Now, in order to do all of this, what needs to happen is the doctor needs to ensure certain documentation protocols are met during each and every encounter. What that means is they have to look at pre-existing conditions, constantly monitor them. For example, if a person is diabetic, then again, in every visit, they have to make sure that the diabetes is being managed properly. If not, then they will need to take measures, and they need to document everything as well using MEET criteria, which I'll explain later. The whole idea of all of this is to actually reduce the overall patient care cost. That's the basic idea behind value-based care. That by actively managing certain chronic conditions, you basically reduce the cost. So yes, now this ties into risk adjustment, as I said, because there's a risk adjustment, there's a score that's associated with every person. That score is called RAF score. risk adjustment factor. Now, the goal is to normalize patients to reflect a patient's health status, of course, because we document each and every condition, right? Again, apart from the conditions, there are certain other factors that determine that RAF score: demographic, age, gender, what's their eligibility, what is their enrollment status, because this is a bit more nuanced in the sense that if a person does not have full medical coverage, then the risk factor would be a bit higher than the other person who has full medical coverage. So plan also has some impact over here when it comes to calculating a RAF score, but predominantly it's mainly about the diagnoses and the demographic of the person. Now, again, the RAF score determines the severity of a patient, which in turn determines the payments. This is more of a push. So in this case, we are mostly talking about the CMS, HCC, and CMS risk adjustment coding. So what happens is people who are on Medicare plans, by the way, 50%, more than 50% people are now enrolled in Medicare Advantage plans, which means that this value-based care has actually exploded a lot in recent years. So this is all managed by CMS. So what happens is at the end of the year, CMS looks at a person's score and then makes a single payment to the providers and insurances. And then those insurance then have to manage that, that one-time capitated payment is actually managed over the entire year, which is why it's extremely important that accurate RAF score is calculated. And as I said, the most important factor in that is making sure that none of the chronic conditions are actually missed. There are other models as well, like HHS model, and even some of the other insurances have their own. I heard there's another one in, I don't know, in San Diego that have their own models, etc. But we're talking about the largest one, which is the CMS. So, yeah. Yeah, so that meat part, nuances in HCC coding. So it's not just a matter of just looking at the conditions. The providers actually have to report and provide certain documentation for each and every conditions, which means they have to monitor it. They have to make sure that whatever is billed and whatever code they have suggested is actually backed by this MEET criteria, which is monitoring, evaluating, assessing, and then treating. So for example, for diabetes, they have to mention things like, oh, the lab results were high, etc. If there's any complication, then they have to make sure that they back the complication if that is due to diabetes, etc. So they cannot just simply say that I treated or gave this person metformin. They actually have to provide the entire thing. What was the evaluation? What was the assessment? And if at the end metformin was suggested, then that is the reason why metformin was suggested. Yeah, problem alone is not sufficient. It has to be the full criteria. Then there are a few other nuances in HCC coding, and that is, I'm sure you're already familiar with ICD-10 codes. So basically, HCC is about ICD-10 coding. Basically, we are trying to codify complete picture of a person's chronic conditions. Now, there are a few nuances over here. As you already know, that ICD codes are structured in a way that it's a hierarchical structure. More severe codes are upstream, then they have more specific codes downstream, etc. The payment also changes according to ICD-10 codes as well as HCC categories. So ICD-10 codes can map to HCC categories, and then each of those categories have a certain payment. So for example, if a person has CKD, chronic kidney disease stage 1, then probably that stage 1 would map to a different HCC category, which would have a lower score, which means lower payment, versus a stage 3, which would be a much more severe condition, which maps to a much higher HCC category and much higher payment. So whenever we're coding, we have to make sure that most appropriate code is actually submitted. not so stage 1 versus stage 3 is a much clearer example, but there are a lot of cases, for example, hyperlipidemia due to diabetes. Now in this case, which one do you code exactly? There's one code, then there are combination codes as well, which is where the additivity property comes into play. So unrelated conditions can also add up. So these are all the nuances that we have to keep in mind while doing HCC coding. Yep. So this is the general workflow of the HCC product that we have. So what happens is now let's talk about putting all of this into a solution. What we do is we have two different types of, we've broken down this problem into two types. One is suspective coding, the other one is retrospective coding. In suspective coding, we do pre-visit data analysis. What that means is people who are scheduled the next day, we pull all their historic data, we process it, we do the HCC gap detection, and it is actually reported back to the provider during their visit, during the appointment. So for example, if a person was diabetic and it was never coded, let's say it's a new code. For example, how do we know? Let's say their HbA1c was high consecutively in the past three labs, but that code was missed or it was never coded. What we do is we would then surface that up with all the information that meet criteria and then suggest it to the provider. The provider then has the option of selecting or making sure the provider looks at the suggestion, takes action. By taking action first, they would obviously do their own analysis, and if it falls true, if everything is correct, then they would just select the code and then they would bill it. This is how you close care gaps in medical coding, right? The benefit of this is much more preemptive. So basically, and there is less chance of errors because it is being validated by the provider. So basically, it is suggestive coding for HCC. And how do we do this? So for example, we have done already, there's some case studies that we've done, but this is the gist of it. If you want to integrate with any EHR, we pull records of patients having appointments in the next few days. We process it, then we dump the results back into Epic. It could be a Fire app, it could be a Smart Fire app, or it could be just another internal workflow of Epic or any other EHR for that matter, because it's all in file format, right? And then the provider just selects codes. It's again backed by explainability analysis, evidence is there. That's the basic idea. And the main benefit is that it substantially increases revenue and improves the accuracy of risk adjustment. The other one is the second workflow is actually retrospective, in which this is after the visit has already happened and probably before you submit to, or even so retrospective has no timeline, but it could be after the provider has already coded, then you do another run on top of it. And when you do another run on top of it, then you look at all the documentation that the provider has already provided. You find codes, you find missing conditions, and you code it. Of course, there has to be a human in the loop because we can't just code and then submit. So this is retroactive. So before suspective is before the visit, retrospective is after the visit. Now, after the visit, before you submit to CMS or to your insurance. Now, there are a few differences in these two, not just the timeline, but also what do we suggest. In suspective, we actually have more liberty or not more liberty. In fact, it is advised to suggest suspective codes as well. Like I said, if let's say if a person's eGFR is a bit abnormal, then the model can look at it and then suggest, oh, this person could be at a high risk of kidney issue, right? Although it could be a one-off thing, but it's a completely valid thing that this is a suspective issue, you might have to look into it, right? Because then the provider would actually look into it and maybe they would suggest the person, oh, go and have another test done so that we can monitor your EGFR score, EGR score over time, and then conclude that condition. So this is where that suspective is. And as the name suggests, anything that is suspective that has enough evidence, we just surface that up. In the case of retrospective, that's not the case. We cannot do that because the documentation is already done. The visit has already happened. Now we have to very strictly adhere to what was done in the visit. In that case, we are much more stringent, we are much more strict, and we don't suggest suspective codes. We only do a second run after the provider has done their coding or medical coder has done their coding, and we try to find anything that was missed by medical coders or the provider. Yeah. The way this works is we have it's kind of like a batch process for the most part, because the basic idea behind all of this is, okay, let me explain in 1 minute. Why do we have to do this anyway? Like, medical coding has already been done. The main point is that using these batch NLP models and LLMs and everything, we can actually process millions and millions of records. For example, in the case of retrospective review, you can literally process in 1 year's data in a few hours and at scale, and then identify codes that were never built. And we've done and seen these exercises, the scenario again and again, where codes are missed because even human coders have a specific error rate, right? Even if it is 5%, 10%, at scale and at large population levels, that error rate extrapolates, and it's a significant missed revenue. That's the reason why we do this in a batch environment, and we process all the historic data so that we don't miss out on anything, because we take delta at the very end. The second point is, so that is for the missing conditions. The second thing is using more appropriate codes. For example, a person could have made a mistake where they've just, for a given condition, they chose a lower HCC category, and enough evidence is there to support a higher. For example, the person had diabetes, and the coder just coded diabetes, but there are tons of other complications that were never coded. Then we can just include that and raise it to a higher level so that more accurate reimbursement can be made. All of this is actually done in batch for the most part. It can be done in real time as well, but for the most part it's in batch, using the NLP pipelines that we have. So we have the core and JSL NLP pipelines that we run. We extract conditions, diagnosis, chunks, map them to ICD codes. Then we have CMS rules on top. For example, how do we look at historic conditions? How do we look at differential diagnoses? There are very specific CMS rules. Every other organization that is participating in value-based care HCC coding has their own set of rules. Even for some payers, private payers, they even have their own rules that they have established over time. So we have to implement those rules. That is the third step. Now there is one step in between extraction of diagnosis and mapping to ICD-10, and that is the reasoning step, by the way, which is not indicated here, but I'm going to explain that. So what happens is we're not just, as I said, in the case of suspected, the chunk might never be there. The doctor might never have said in the past historic notes that the person is diabetic, but the value is high, right? So that is where we have a reasoning layer supported by RAG, which actually looks at all the chunks and the entire note, and then does two things. One is it surfaces suspective codes. The second thing it does is it attaches evidence to each of those conditions. That's the reasoning there, because as I explained earlier, we cannot just simply say E11.9, this is the code. No, why was this code suggested in the first place, right? So the model actually does all that reasoning, and which is why this entire paradigm is called evidence-based care, right? So, or value-based care, also evidence-based. So evidence needs to be there. That is where we have that reasoning there. Then we have once we get the codes and we're sure that the codes are correct, there's nothing, no false positive, maybe 1 or 2 false negatives, or very less false negatives, but mainly no false positives, because that can lead to some other issues, which we'll discuss later. Then we add in the demographic information, plan eligibility information, and then we calculate RAF score. Mainly when we do this properly, we should get a significant RAF lift. The RAF lift is the term in medical domain that is usually used, that how much lift is being achieved without NLP versus NLP, and that is very simple. How many new codes were identified, how many valid new codes were identified, and that is the actual lift, because that increases the RAF score, right? Now, how does this actually work, or what does the UI look like? I told you that this is a bad job, which is correct, but basically we have a UI for this as well, and this is for the retrospective review for the most part, which medical coders can just use. So this is a medical coding platform that has the HCC retrospective engine built in. That's the basic idea. So for example, I can just create a new project, demo. I can just upload, assign to users. I think demo is already created. And I can, upload tasks. I've already done this, but I'm just showing you. Let's just do this, upload tasks. So it will run in real time and try to predict, try to find. So what did I upload? The input packet is actually nothing but basically medical notes of each patient. So they're like, I don't know, 4 or 5 medical notes. Now here, so the prediction was done, the model ran, and it identified these things. So it identified all the 8 ICD-10 conditions with evidence. So look, right? So we have 2 conditions in this encounter, CKD stage 3 and I-24/9 acute heart disease, and those are being suggested here with evidence. So the user can just, what the medical coder would do is they can just go in, look at what is already predicted on the right side and say, okay, this one is done, the other one is done, okay, maybe this one is not done, so they can just delete it, or they say, oh, I have a better code in mind. Maybe they would want to do something like, I don't know, I-24/8, if that's the, yeah, maybe they want to change it, and then they can just save and submit. Or they can, let's say, they can just delete this and say that this one was incorrect. They can make their changes right here. So they can just add code, and they can do CKD again, whatever. So their smart lookup is already baked into the tool. As you can see, I was just typing abbreviations. It just works. Synonyms and all of that stuff is there. The 329 is actually the HCC category, and 1831 is actually the ICD-10 code. And then they can just save and submit, very simple. And then it would be, and we can have multiple versions. This was my version. Multiple people can collaborate, so we know that this was the model's version. This is what I did, and some other user can just go in and do their own stuff if this project is shared with them. And then we can submit, and it would be like, maybe we did not. Okay, so we need to approve. Okay, so yeah, all the conditions, by the way, need to be either approved or deleted. There cannot be any condition that is left unattended. So now we know that this one is actually submitted. We know which version was submitted, etc. Then we can just move to the next task, and that's it. So for example, this is again CKD. Maybe we have another one. Yeah, this one is this. So look, evidence, right? So it picked evidence from here. And users can even add in their own comments, etc., etc. And they can just export, once they're done with this project, they can just export this, or it can be dumped into the database, and then we can calculate RAF. So yeah, and then we can check over here. We have some dashboards that how many codes were correct, how many were incorrect, what was the average charting time, etc., etc. All of these things are already available. So this is the HCC tool. Basically, this is a general medical coding tool that can be used for literally any type of medical coding, but we're using it for HCC because the backend is already HCC. Okay, so this is HCC part covered. Again, the idea is that we find more accurate. We don't miss out on any conditions. We find as accurate codes as accurately as possible, so that the RAF score is as accurate as possible and no revenue is missed. Main benefits is when we run it at scale. So that was the summary. Now we can go to look at the other tool, which is the RADV tool. So basically, what is RADV? It ties into the same HCC ecosystem or the same area. It is risk adjustment data validation. So risk adjustment factor, if you remember that RAF score, this is essentially the validation of the same idea. Basically, what happens is CMS has, and by the way, starting this year, CMS has significantly increased their audits. So basically, this RADV is audits by CMS. So for example, a provider and a payer submits 10 different conditions to CMS, and they got, I don't know, $5,000 or $500,000 for those conditions for the entire year. Now CMS, obviously they need to do their own due diligence. Like they also need to look at if the codes were submitted were even valid or not, which is why I said earlier that every code needs to satisfy that meet criteria. That satisfaction of that meet criteria is actually what we do in RADV. If you use the same HCC model, which we just looked at, that meet criteria should be already satisfied, but this is for a separate exercise where even after submitting to CMS, let's say they are auditing 10,000 different plans, and you get an audit for the codes that you have submitted, you won't use the HCC tool. You would actually use this one because you're not doing coding anymore. You're doing RADV, and there are some rules to RADV. In addition to that meet, there are some additional things like, is the document signed? Who was the provider? Date of service is aligned or not, et cetera, right? So basically, this risk adjustment program is to confirm that the documents submitted, the diagnosis submitted, are actually supported in the medical record, so there's sufficient documentation available. This is to address if or ensure that there are no overpayments in medical advantage plans, and they are actually at medical. So this is a different thing, but they actually occur at contract level and by payment year. So for example, this year they could be looking at the codes that were submitted last year, etc., or maybe even the year prior to that. So what happens if somebody, just to get more money or just to get more payments from CMS, what if somebody just does just codes in unnecessary conditions? Then that results in penalties and clawbacks because CMS would validate each and everything, right? The reason why we're emphasizing on this is, as I said, starting 2025, there's significant escalation in audits. We've heard that I think majority or nearly every medical advantage plan would actually be audited, which means millions and millions of audits, which means there needs to be an automated service that does this, that does the RADV stuff. Now, in RADV as well, we have two workflows. Again, how we've structured this problem is into two workflows. One is proactive, the other one is reactive. Reactive is what I'm talking about, where you actually get a notification from CMS that, okay, we are auditing these plans. That is reactive. Proactive is before you even submit to CMS for this year, you actually run it through the engine, the RADV engine, and you just make sure that everything is working proper, everything is coded properly. You're not doing overcoding, you're not doing undercoding, etc. Again, all of this could be done at scale. That's the main point of this, right? So you just run it through your entire population just before you're submitting to CMS, and you can run multiple runs. So for example, you do one run and you see tons of issues, probably you check it out why, and but this is what we call mock RADV sampling. So you can just run it through your entire population to see what is the error rate that you have in your submissions. That is proactive, meaning before you submit to CMS. Reactive is after you submit. In both cases, by the way, the only difference is it's the same tool, it's the same philosophy. The only difference is before you submit to CMS, you can obviously make some changes and make sure you don't run into penalties and further clawbacks. how does it actually work? So there's again a UI. This one is a much more elaborate UI because CMS requires certain types of audit packets, and they require certain types of, they require a specific format for submission, which is PDF based. So basically, whenever you submit into all the PDF files and the codes to CMS. This tool that we have built is actually built around that. So you can upload the same audit packet to this tool, and you can export that audit packet and then submit to CMS. So basically, you upload either via API in batch or using the UI. You upload the entire audit packet, either it's internal mock audit or real audit, and the model would just run through all the codes, all the documentation. OCR is already baked in. Yeah, and we would the model would actually try to validate and substantiate each of the codes. So it would look at the codes, look at the documentation, and check if enough evidence is present. If not, then it would flag those codes. It would say that no, there's no evidence for them. And you can process big files, like hundreds of thousands of pages. That helps because this is usually what happens. These files are long, and let's say it's a 100-page file, and you only have one code. Then a human would spend, I don't know, 5-10 minutes going through that entire file. The model can just do it, and yeah, then we just have a user in the loop workflow, and then we can just export those packets and submit to CMS. How does it work? Let me actually log out from this one. And again, all of this tool is actually something is designed to be deployed in-house. The backend models are based off of the same technology that we have, plus more. So basically, the philosophy is still the same. You don't need to send your documents out. You can run your entire CMS submission before sending to CMS. Just run it through this engine and validate the results. You can, and this is a human in the loop process as well. So for example, I just created a dummy project, and I can just go in. Let's say we had 2 enrollees. Each enrollee is actually one patient. So let's say this was one enrollee. These were their ICD conditions that were submitted to CMS. Let's look at this. So 3 conditions and 3 files. Okay, so this code is actually valid. Why? So this is coming from the model, by the way, because the model says that, okay, in page 1, this E11.8, in page 1 has significant, evidence. So, and I can just click on this, click to view in PDF, and it would just take me there, right here. Right? And there's another file in which we had we had some significant evidence for the same condition. I can just click on this and see. So as a user, I can just ensure that what the model has predicted is correct or not, right? And I can even edit this. I can say, no, I see a different evidence, etc., etc. I can even unlink this. I'm like, no, this was invalid. Maybe even this is invalid. Then in that case, I'm like, okay, this code was never, let's say that this was an error from the model and this was an invalid code, then I can just make those changes. This was never predicted by the model. Why? Because there is no such, there's no evidence for this condition, but let's just say I say that I found something. Let's say the user says it, then I will be like, okay, in this thing, I found evidence in this page, in this file. And then we can just link this, right? So let's just say, okay. So we can link, unlink evidence, everything is mapped at page level. If required, this can even be increased to paragraph level, but for now, we've kept it very generic to page level. But yeah, so for example, this one is actually in 2 different files. Right? One is in this, and the other one is this. We can just check. And it even tells you over here that this file has these ones, this one has this one has this. So associated ICD-10 codes. Once I'm done, I'm like, okay, save and then submit. Then I could just go in and it's completed, right? I can go to another task and then do the same. And for example, we have this large file which 12 pages, and we just go to the very end. So as you can see, that this is, by the way, a redacted file, which means this is a scan file. And we have, in this enrollee, we have, I don't know, 7 codes, and one of them is invalid. The model did not find any evidence for this, but for the other ones, it just linked. So I was just showing you this. This one is a long file, and we just literally, it just takes us there, right? Because reason for visit is this, right? So this code is valid, right? Yep. This one belongs to 2 files, and in this file, it has significant evidence in multiple places. Like there's history, there's treatment and medication that is being administered, etc. The HbA1c is high, so for we have evidence in multiple places for this specific condition. Yeah, and then once I'm done, I can just save and submit, and let's just do this. And I can just go to export, and I can then see that, okay, 2 enrollees were in this audit packet. There were 9 files in total, and out of which 6 had codes in them, because obviously when you submit to CMS, you will not be submitting files that don't have any codes, right? And not only that, you also have a limit of 2 files per HCC. That is also one limit. So when you export, it would select the best ones for you. And there were 11 total codes, out of which 8 were valid, 3 were invalid, etc. And not only that, you can actually go into settings and change the version of HCC CMS HCC version, because it depends. It's updated twice a year for the most part. Then you have to look at for which payment year are you running this audit for. Let's say if it is for 2024, then you would be using a different HCC version. It could be, the payment year would be 2024, version could be either V24 or V28. So all of this is configurable. That's the main point. And then you can just download this audit packet, and it would download an audit packet for you with complete chain of custody. What that means is who did what. So whatever we have already done over here in tasks, that all of this is being logged. I was the user who created the project, so there's complete provenance. Who created the project, who did what in this project, everything actually gets exported as part of the audit packet. It's not a hard requirement by CMS, but we still do it for transparency. And like I said, all the files that are invalid, or not invalid, but the files that are redundant, that don't have any codes, we don't care about them. We don't export it in the export audit in the export packet, because we don't need to submit them to CMS, right? So only valid files and valid codes would be submitted. And then you can just take that exported packet and send to CMS once you're happy with it. Yeah, so that's the basic idea behind these 2 tools. Both of them are in value-based care. One deals directly with RAF score missing. So the first tool that I showed you deals directly with RAF score and finding missing conditions, making sure that the coding is appropriate, making sure that, again, at scale, that no condition is missed or appropriate conditions are selected, because we've deployed this in customer environments, and we see this again and again, that when we run it at scale, even small errors, and we pull those missed conditions, those actually translates to sometimes millions and millions of dollars in real value. So that was the first one. The second one is, if you're submitting to CMS, either you can do it first in-house to run mock audit cycles and make sure that you don't have any issues in your submission, or even if after you get it from CMS, you get the export, you get the notification, then you can just ingest this into this tool. One additional thing is that when you actually get a notification from CMS, those are specific types of files. I think those are called CSS or CLS files. So we also have adapters for that. So instead of uploading, like you don't have to download and then upload. We have an adapter or a connector that would directly pull data from CMS and just ingest run it in batch, and give you results in a nice UI, like what you're seeing. And yeah, then a user in the loop can, a human in the loop can actually just validate it. Look, first you can just look at the results, see what is the error rate, which you can very easily do here. And there is also an API available for this, so you can whatever. Look, so you can just see how many codes were invalid, right? It's right here, 3 codes. So this way you'll be able to see how many codes are invalid, even in your internal mock audits, and you can literally see which files, which codes, etc. So that's the basic idea. Yep, and that's it for this session for today. I think you'll be. Thank you for joining in today. I think this is the last session. Tomorrow will be. We'll have another. We'll have an additional 4 sessions. But for today, yeah, thanks for joining in, and have a great day.